Sorry for for the inconvenience. So this is Francesco Cartella from Sony Corporation, and I will pitch now our poster. Thanks for the opportunity. So we can go to the next slide. So with the increasing popularity of applications based on artificial intelligence, new security threats are emerging. One of these is adversarial attacks, where imperceptible changes are applied to input data to obtain the so-called adversarial examples that induce the AI system to produce an incorrect classification output, which is advantageous for the attacker. While adversarial attacks are increasingly explored for image classification, literatures and tools dedicated specifically to adversarial attacks on tabular data are limited. For this reason, particular attention should be put in all the applications that employ AI techniques to deal with transactional data, like fraud detection in banks, web shops, and so on. The goal of this work is to make adversarial attack techniques effective also when applied to tabular data. And our focus is on use cases where data are highly imbalanced, like fraud detection. So we can go to the next slide. So at this purpose, 3 attacks algorithms have been considered and modified to address some structural differences between image classification and fraud detection. In particular, properties like data imbalance, bias in the model, heterogeneous type of data, editability, and imperceptibility have been addressed with innovative solutions. The experiment we made on a risk assessment use case demonstrated that while prior to our modification, the algorithms were unsuccessful, we obtained a success rate of 100%, improving imperceptibility by up to 64% with respect to the state of the art. Attack transferability has been also demonstrated on a real production system, where a success rate of 13.6% highlighted the fact that properly designed adversarial attacks represent a real threat for systems currently in use. So of course, you can discover more details in our paper at our poster. So if interested, I will see you there. Thank you very much.
Great, thank you, Francesco. Next one is correct by construction multi-level classification networks.
Hi.
Hello, Eleanor.
Hi. Hi, everybody. Can you see my screen?
Yes.
Okay, nice. So hi, everybody. I'm Eleonora Giunchiglia, and I'm presenting actually coherent by construction multi-level classification networks. So these are networks that are built for multi-level classification problems, which, as we can see from the picture, are problems in which every object can be assigned multiple labels. A very interesting class of these problems is given by hierarchical multi-level classification problems, where basically the labels are organized as a tree or as a DAG. Why is this class of problems particularly interesting for us? They are interesting because in order to make predictions trustworthy or actually usable by the user, it's a requirement of the problem itself to make predictions that are coherent with the hierarchy constraint. What does this mean? It means that if I predict these 2 nodes, then I also need to predict all the ancestors up to the root. So in this work, we asked ourselves, why do we have to limit ourselves to such simple constraints? And so we introduced what we call logically constrained multi-level classification problems, which basically are just multi-level classification problems with a finite set of constraints expressed as normal rules. This means that now we can write, for example, the constraint that if the label sun and the label moon are assigned to an object, then we also must assign the label cloud. Or we can write that, for example, if the label sun and not the label cloud is assigned, then we must also assign the label moon. So for this class of problems, we have actually built our own model. And this model has been built following 2 basic goals. The first one is that this model must always output predictions that are coherent with the constraints. So these constraints must always be satisfied. And the second one is that the model must in some way exploit the background knowledge contained in the constraints. So our model presents 3 basic features. The first one is that the predictions are indeed guaranteed to be coherent with the constraints. The second one is that it's easily implementable on GPUs. And the third one is that it beats state-of-the-art model on the hierarchical multi-level classification task. And it also beats all the state-of-the-art models built for multi-level classification problems on which the constraints have been imposed as a post-processing step. If you want to know more, please just come by and talk with me at the poster. Thank you.
Great. Thank you, Eleonora. We have a third one here, which is classification confidence scores with point-wise guarantees. Do we have the presenter for this?